Hello and welcome to this video on an exam walkthrough. This is for the Edexcel Unit 1 Core Principles of Chemistry. This was the May 2015 paper, or the Summer 15 paper. My name is Chris Harris. I'm from AlleryTutors.com. I also run a YouTube channel called Allery Chemistry. Also there's podcasts as well involved, and also a set of teaching and revision resources as well. It's all found on AlleryTutors.com, so go and take a look. So this video is basically aimed to just go through the past paper. Obviously, the mark schemes are very important. They show us the answers, etc. But what they don't do is they don't explain why it's the answer or give some kind of understanding. So the whole point of this is to obviously make sure that you get the answers right, but also to understand why they're right, because through understanding you can improve on your technique, and you can improve your learning as well. So so let's make a start. Let's crack on. So we're going to look at the first one. I should also point out, make sure you read the instructions really carefully. I know that sounds so daft, but you've got to make sure that you give the right indication as to the right answer. If there's any ambiguity, it could lose your marks. So make sure you do read the instructions carefully. So question 1. It says, which molecule does not exhibit EZ isomerism? Okay, so with EZ, you always get a double bond, and what you're looking for is two groups that are the same, that are opposite the double bond. So that means top and bottom when I say opposite. So that's what we're looking for. If we have the two groups that are on the same carbon, that doesn't display any EZ. So let's have a look at these examples. So you can see this one here. Here's an example. Look, there you got two same groups, two CH3 groups, and they're opposite the double bond. So that means that will exhibit EZ isomerism. If we look at B, you can see we've got two groups there, but look, see these two groups are bonded to the same carbon. That means there won't be any EZ isomerism. So that one's actually doesn't exhibit EZ, but let's just look at the other ones as well. These two, there's your two same groups, two hydrogens. They're bonded on different carbons, so that will display EZ. And there's your two groups, and methyl as well. So they're on different carbons, so that will display EZ. So the answer here is B. That's the only one that won't display an EZ. Okay, question 2. What is the systematic name for the compound with the following formula? Right, now the trick here is to find the longest carbon chain. Okay, now you might look at that on the face of it and think, well, my longest carbon chain's there. 1, 2, 3, 4, 5. But it isn't. You've actually got this ethyl group isn't a branch. This can be included in the longest chain. That is your priority. Just find the longest carbon chain. So here, obviously, we've got 2 there, 3, 4, 5, 6. So the longest carbon chain is 6 carbons. That means it's going to be a hex. So we're either looking at A, C, and D. A and B include pent, so it can't be them ones because we know it's not pent. So we've narrowed it down to C and D. Now what we have to do is look at the number of carbons. Now we need to number this carbon chain with the lowest numbering system possible. So let's start on the left hand side. So let's imagine if this is carbon 1, that's carbon 2, carbon 3, carbon 4, carbon 5, and then carbon 6 at the end there. So let's imagine we're using this numbering system. You can see that we've got a methyl group hanging off the second carbon, and we've got a methyl group here hanging off the fourth carbon. So numbering this way would give us 2, 4, which is that. Or if we numbered the other way, let's just do it this way as well. Let's say we'll call that 1, that 2, that 3, that 4, that 5, and that 6. Now if I did it that way, that would mean that this would be a methyl group on the third carbon and a methyl group on the fifth carbon. So that would give 3, 5. Now, the rules of IUPAC basically tell us that we've got to have the lowest numbering system. So if I add 2 and 4 together, it's easy maths really. If I add 2 and 4 together, we get 6. And if I add 3 and 5 together, we get 8. And you can see 6 is smaller than 8. So that means that the numbering system at C is the answer. So always go for the lowest numbering system. Okay, so let's get rid of that. So it's not going to cause too much confusion. Okay, so the answer to this one is C. Okay, right, next question. So this is question 3. So question 3 says, which of the following molecules is formed on adding bromine water to ethene? Right, now, because this is bromine water, not bromine, we get slightly different products. Basically what you get is an alcohol group at one side of the double bond, and you get the bromine atom attached on the other side of the double bond. So what you get is an OH and a Br. So we get an alcohol and a haloalkane. So we need to make sure that we're writing down the right thing. Now you can see here, bromoethane would be true. If it was pure bromine and it wasn't bromine water, you would get bromoethane. Ethane 1,2-diol. Diols are formed when you oxidize them using an oxidizing agent. This is not an oxidizing agent, so we're not using that, something like permanganate. Ethanol, that wouldn't be formed. There's no bromine on there. Bromine's definitely out of the molecule, so it's definitely not that. So the answer is D, because that has the bromine and the alcohol group on there. Okay. Right, question 4. A section of a polymer is shown below, so there it is. What is the monomer for this polymer? Right, so a monomer is something that makes up polymers. You join them together. Monomers are always alkenes if it's an addition polymer, like this one will be. So you're looking for an alkene, basically, a double bond. But the identification of the repeat unit is really important, because that's going to show us what the monomer could be. So if we look here, you can see the repeat unit is there. That's a repeat unit. That's another repeat unit. So we're looking for a monomer that has that structure there. That's what we're looking for. Now it must have a double bond between here. So we're looking for a molecule that obviously originally had that double bond. So it can't be A, because that doesn't have a double bond. This isn't true. Yes, it has double bonds, but it looks nothing like this compound here. This is obviously just joining both of them together. So we're only looking for one repeat unit, remember, not the whole thing. So it's not that one. If we look at C, it looks likely. There it is, C2H5, carbon, CH3, CH3, CH. There you go. It looks exactly like what we're looking for with the double bond. So that is the monomer. But let's have a look at the other one as well. This one's got CH3, CH3, C2H5 and H. This one's just flipped around. But you can see clearly that CH2, C2H5 is on the bottom left-hand side. And that one matches that one, so it can't be that one. So the answer is C. Nice and easy. Okay. Right, on to the next question. Right, question 5. So we're saying which of the following equations has the correct state symbols for the reaction of dilute hydrochloric acid with magnesium oxide? Okay, so we're basically looking for the correct state symbols, obviously. You really need to obviously know these state symbols. It's important. I suppose the first thing I need to say is that acids, hydrochloric acids, are always aqueous. Acids are always aqueous. They're never liquids. So they're the ones that we use in A-level anyway. So these ones we don't use. We can discount C and D straight away because acids are aqueous. They have H+ ions which dissociate in water in solution, so they're always aqueous. So that's these two, which is A and B. And then we need to obviously try and whittle down what we've got. Now, the only difference here is the magnesium chloride bit. All the other state symbols are the same between them two. Magnesium chloride is soluble. It forms a solution. So the answer is aqueous. So the answer is B here. And obviously you form water as well. It's not a precipitation reaction. So this one is B. Okay, question 6. This question is about the reaction between sodium carbonate solution and dilute nitric acid. So you see we've got the equation here. Now we've got to look for the ionic equation for this reaction. Now what we're looking for is basically the ions that get involved with the reaction and actually change. We have a difference in the ions. Anything that remains unchanged, we're not really interested in. So this is how we're identifying which ions are relevant. The other ions are what we call spectator ions. They are there, but they don't get involved with the reaction. So in this case, it's a bit like spot the difference, really. We're looking for a difference here. Now, if you see the sodium, let's try and discount some of these. Start with the sodium first. There's sodium on the left. There's sodium on the right. Now, sodium is compound. It's in a compound here, and it's in a compound here. Sodium hasn't changed. It hasn't really changed in any shape. It's the oxidation state is +1 here. It's +1 there. So the sodium hasn't changed. So we can ignore it, and we can say it's a spectator ion. Yes, it's there, but it's not getting involved with the reaction. Look at the carbonate. Carbonate was CO3 here, but there's no carbonate on this side. It's been decomposed. It's changed into something else, which is carbon dioxide. So the carbonate ion is actually pretty relevant. So I'm going to emphasize that in green. So it's obviously broken down into something slightly different. Okay, then look at this bit, hydrogen. So this was bonded to a nitrate ion, HNO3. Now the hydrogen has physically got involved with the reaction because it's being used to form a different compound now, which is water. So it was in nitric acid and now it's water. So actually the H bit is going to be important, and so is the water bit as well, because the H has been used to form the water. If we look at the nitrate bit next, now you can see the nitrate, there's NO3 there, and there's NO3 there. Nothing's happened to the nitrate. It has bonded to something else, but it hasn't physically broken down. It's pretty much the same. So we can just say we can ignore that, and the nitrate is just a spectator ion. So then all we have to do is look at what we've got left. We've got a carbonate, CO3. Now this as an ion would be CO3 2-. This would be 2H+, because that's the H+ bit there. And then obviously we've formed our carbon dioxide and water, which are these two, which is just the same. So we're looking for a reaction with that in, and you can see the one which is going to give us that is the C. There's your carbonate plus H+, gives CO2 and water. All the rest of them give spectator ions. So that's the answer there. That's the Ionic equation. So let's just put a cross in there, which is question 6. Okay, so just look out for ones, look out for like significant changes really. Okay, part B. What is the volume of carbon dioxide produced from the complete reaction of 0.1 mole of nitric acid at room temperature and pressure? 1 mole of any gas occupies 24 decimeters cubed at room temperature and pressure. Right, okay, so we've got a bit of maths here. Right, the first thing, we're going to work out obviously the volume of carbon dioxide produced, but to work out the volume we need to work out the number of moles first. Is that saying, if in doubt, work out the moles? Because if you know the moles, you can work out pretty much nearly anything. Right, let's do this in green, shall we? So we're going to go for the moles. Now you'll have to remember this equation. We're going to use the volume in decimeters cubed, and that's going to be divided by 24.0, because this is 1 mole of any gas occupies 24 decimeters cubed. So that's how we're going to work out that's how we can use the moles. Sorry, because we don't actually need to work out the moles because we've got the moles already. So that's my mistake. But we need to work out the volume. So we're going to rearrange this equation. So if we rearrange it, we get the volume is basically the number of moles which we have times by 24.0. Okay. So now this is the tricky bit, because actually, yeah, we do know the moles of nitric acid, but we want to work out the number of moles of your carbon dioxide produced. Now, if I go back up here, you can see there's the reaction that we're using. It's told us we have 0.1 moles of nitric acid. There's nitric acid there. But we want to work out how many moles of carbon dioxide we produced. Now, if you look at the ratio, that's a 2-to-1 ratio. So we know that we have 0.10 moles of this. So the number of moles of carbon dioxide must be half that. So what we're going to do is going to take 0.10, let's put a point on there, divided by 2. Okay, so that tells us the number of moles of carbon dioxide that we formed, times that by 24. And what you should get, if you put that into your calculator, you should get 1.2, and that's obviously in decimeters cubed, because that's the volume we're using, or that we're trying to work out. So the answer for this one would be A, 1.2 decimeters cubed. Okay, part C. So we've got part C. So what volume of sodium carbonate solution of concentration 0.500 moles per dm cubed would be needed to completely react with 25 centimeters cubed of nitric acid of concentration 0.250 moles per dm cubed? Right, there's a lot of numbers there. Okay, so we need to work out, let's work out what we need to do. We need to work out the volume of sodium carbonate. Okay, now they've given us the concentration, 0.5, so we'll probably use that later on in that one. But we know this one though, 25 centimeters cubed of nitric acid of concentration this. Now because we know a volume and a concentration, guess what? We can work out the moles, and that's exactly what we're going to do. So we're going to work out the moles of your nitric acid first. Okay, so we're going to write this in green. So this is the moles of HNO3, that's nitric acid. And this, remember, is going to be the concentration times by the volume. Remember, the volume is going to be in decimeters cubed. So the concentration is going to be 0.250 times that by the volume, which is 25. Now that's in centimeters cubed, but to get it into decimeters cubed, I need to divide it by 1,000. If I just put times 10 to the minus 3, that is exactly the same as dividing by 1,000. It just keeps it a little bit neater. So if I put that into our calculator, I've already pre-worked this one out. So the answer should be 6.25 times by 10 to the minus 3. Okay, so that's the number of moles of nitric acid. Now what we need to do is we need to work out the volume of sodium carbonate. Okay, so the volume of sodium carbonate, which is Na2CO3. Okay, right, what we need to do, well, let's go back. There's our nitric acid, there's sodium carbonate. Look, it's a 2-to-1 ratio. So the number of moles of nitric acid and the number of moles of sodium carbonate, is going to be half that of whatever the moles is of nitric acid. Now, I've worked out the number of moles of nitric acid as that. So basically, it's going to be that number divided by 2, and that'll tell us the number of moles of sodium carbonate. So to work out the volume of this, it's going to be moles divided by the concentration. Okay, we've just rearranged that equation. That's all we've done. And that's going to be 6.25 times by 10 to the minus 3. Divide that by 2, because that's going to tell us the number of moles of sodium carbonate. Divide that by the concentration, which we worked out was 0.5, because it told us in the question. Okay, and then we put that in our calculator, and we should get 6.25 times by 10 to the minus 3. Okay, so this is obviously the amount in decimeters cubed. Okay, that's dm cubed. So to find that into centimeters cubed, we just multiply that by 1,000, and we should get 6.25 centimeters cubed. So if we look for our answer, it should be A. Okay, so there's a bit of maths there. Okay, nothing wrong with a bit of maths. Right, question 7. Question 7. Lithium reacts with water to produce hydrogen. So there's our reaction there. In an experiment, 0.069 grams or 0.01 moles of lithium produced 90 centimeters cubed of hydrogen at room temperature and pressure. What is the percentage yield of hydrogen? Right, and we've got the 1 mole of any gas, etc., etc. So that's a standard reaction. Right, this is quite tricky because we've got to really think about obviously what's happening here. Okay, so we'll start with, let's look at, obviously it's talking about lithium and it's looking at hydrogen. So we're just going to forget the rest of the ones in there. We're just going to focus on lithium and hydrogen. Right, so what we've been told is we have 0.01 moles of lithium. Okay, now half the amount of hydrogen, which they've told you, is basically half the number of moles of this. So if we take this and divide it by 2, we should get the number of moles of hydrogen. So that's going to give us 5 times by 10 to the minus 3 moles. Okay, so that's the first thing. Then once we've worked out the number of moles, we then need to work out the volume of this gas, and we do that by multiplying that number by 24. So if we take, if we do volume equals 5 times by 10 to the minus 3, times that by 24, and that's going to tell us the volume of hydrogen gas that we can produce. And so that should be, again, all this is going to be in decimeters cubed, so it's going to be 0.12 decimeters cubed of hydrogen gas that we can produce. Okay, so we need to work out obviously what that is in centimeters cubed, because this is going to tell us how much we should produce in theory, in theoretical amounts. So effectively that is going to be 120 centimeters cubed. Okay, so this is going to be 120 centimeters cubed of your hydrogen gas that is produced. So now all we have to do is we just need to work out our percentage yield. So we know that in this reaction, in this experiment, we produce 90 centimeters cubed of hydrogen. In theory, we can produce 120 centimeters cubed. So this is the maximum we could produce if the reaction went perfectly in a perfect world. So all we do is we do the actual amount that we collected divided by the theoretical amount, times that by 100, and we should get a yield of 75%. So the answer is C. 75%. That's quite tricky because you had to do quite a bit there. You have to work out the moles of hydrogen and work out the theoretical yield. Okay. B. Which of the following is not a possible reason for the yield being less than 100%? Right. So sometimes, obviously, we can get a yield that we can lose some products, etc., or we might get some things which are unreacted. So if we have a look on here, we've got part A, some oil remained on the surface of the lithium. That could be a possible reason. The oil would obviously prevent full reaction of the lithium, so that could be a possible reason. If we look at B, hydrogen gas is very soluble in water. That's not really going to make much of a difference. The hydrogen's a product. It's not going to reduce the amount of yield. It's just in the water. So actually, that one's not a possible reason. So the answer is B there. But let's just have a look at the other one as well. The layer of oxide was present on the surface of the lithium. That would actually, again, prevent, a bit like the oil, it'll prevent the reaction of lithium, the complete reaction. So yes, that could reduce the yield. And then some of the hydrogen gas escaped collection. Yes, because obviously if you're losing some of the products, then that'll give you the impression that it hasn't actually, or you haven't actually produced all of the product that you need. So the answer here is B. The fact that it's soluble in water makes no difference really. As long as it doesn't escape, that's the main thing. Okay, right, question 8. How many moles of atoms are present in 240 centimeters cubed of carbon dioxide at room temperature and pressure? 1 mole of any gas occupies 24 decimeters cubed at room temperature and pressure. Right. Okay, so they use that a lot, don't they? Right, okay. So, alright, so this is relatively straightforward. The key thing here is atoms, though. Look what it says. Okay, really kind of focus in on that. You've got to make sure you kind of read these things really carefully. Okay, so, so what we need to do is just work out the number of moles. Let's use this in blue this time. Going to go all multicolored. Okay, so we've got the number of moles. Now, we've been told that we have 240 centimeters cubed, okay, of carbon dioxide at room temperature and pressure. So that's exactly what we're going to put in there. 240 centimeters cubed. So the number of moles, remember, is the volume of gas that we've produced divided by the standard. Now, because this is in centimeters cubed, I'm going to convert, instead of just using 24, I'm going to put 24,000 because that's in centimeters cubed. So basically 1 mole of any gas would occupy 24,000 centimeters cubed at room temperature and pressure. So I've just converted that into that. Now, if you put that into your calculator, you should get a value of 0.01 moles. Okay, so this is the number of moles of gas that we've produced. Remember, this is the moles of CO2. It didn't ask for the number of moles of CO2 though. It's asked for the number of atoms, number of moles of atoms. Now you can see here, carbon dioxide is made of 3 atoms, 1 carbon and 2 oxygens. So all we have to do is we take that number, multiply it by 3, and we should get 0.03. Now, I reckon a lot of people might have gone for A for that one, thinking that would be the answer, but it's actually not. The answer is D, because it's asking for the number of atoms. So it just pays. Make sure you're reading the question really carefully. Okay, so that's part D. All right, okay, so on to the next part. So this is question 9. So what is the percentage by mass of nitrogen in ammonium nitrate? And we've obviously got all the molar masses there. Alright, okay, so this shouldn't be too bad. Let's go for green this time, sorry. Right, all we have to do is just work out how much nitrogen's in there. So if we take the molar mass of nitrogen, in ammonium nitrate, you've got 2 nitrogens. You've got 1 there and 1 there. So we're going to do, nitrogen is effectively 2 lots of 14, because we've got 2 of them. And that's going to give us 28. Okay. And then all we have to do is just basically work out the total mass of everything. So this is of, obviously this is of ammonium nitrate. Okay, so we're just going to add the whole lot up. So it's going to be, what, 14 plus 4, which is because of the 4 hydrogens, plus another 14 for the nitrogen there, plus 3 times 16 for the oxygen. And if we add all that up, we should get to 80. And then all we do to work out the percentage by mass, we do 28 divided by 80, because that's 28 is the nitrogen, 80 is the total mass. Obviously times that by 100, and we should get 35%. Okay, so the answer should be D. It's D again. Okay, I've had a lot of D's. Right, question 10. Right, the first 5. Successive ionization energies for an element J in kilojoules per mole R. Right, so we've got all these numbers here. Now what we're looking for is a big jump. We're looking for big jumps. So this is where we've got we're removing an electron from an atom. We keep on removing an electron from it. And big jumps suggest that when you're taking an electron, or suggest that you are taking an electron from a shell that's much closer to the nucleus. So you've taken all the outer ones and now you have to dip into a one much closer. So that gives us an idea of how many electrons there are in the outer shell. So if we look at this one, you can see that we've got a relatively big jump. That's quite a small jump between the first and second. But look at the jump there. That's a big jump from the second to third. Now what that's telling us is that actually we've removed 2 electrons from this atom, and to remove the third one we're having to go into a shell much closer to the nucleus. So this tells us that this atom must have 2 electrons in its outer shell. In other words, it's a group 2 element, whatever this is. Obviously they're calling it J, but obviously that's not an element. So we need to think of a compound that would form in group 2. So you're looking for something like JCl2, because if it's in group 2, it can bond to 2 chlorines. So this would be the answer here, which is JCl2. So the answer is this one, is B. Okay. Number 11. Which of the following is the correct order of increasing melting temperature of elements in period 3? Alright, so we're looking for things with a really high melting temperature. Straight away I can detect that we have, let's just use this in blue, silicon is really high melting point. It's got one of the highest melting points in period 3. So because this one is obviously the highest, then the answer's got to be A. Silicon should be right at the end there. So make sure it says in order of increasing melting temperature. So make sure it is actually the increasing one. Sodium's quite soft. You might have seen it. You throw it in water, it explodes. It's quite soft. You can cut it with a knife. Magnesium, you might have used the ribbon. You can twist it between your fingers. The magnesium ribbon. It's a little bit harder than sodium, but not as hard. Aluminium is a little bit more difficult. Basically, the metallic structure here. This has got a quite a weak metallic structure. There's only 1 electron and 1 positive ion. So the attraction between the delocalized electrons and positive ions is quite small. Magnesium is a little bit bigger and aluminium is bigger still. So the attraction gets stronger and stronger, and that strengthens the bond, which increases the melting temperature. And silicon's got the highest of the lot. It's a giant covalent structure. So that's why it's A. Okay. Right. Question 12. Okay, so question 12, it says, which one of the following elements undergoes the change in electronic configuration shown when it forms the stated ion? Okay, so what you need to do is look in the periodic table. Now, if you see on the periodic table, the electron configuration for this, that's 1s2, 2s2, 2p6, 3s2, 3p6, it should point to phosphorus. Okay, now, if you add 3 electrons, if you look at the difference, this is the ion. Look, the ion has effectively gained 3 more electrons. So that must mean we have to form a negatively charged ion because we're gaining negative electrons. Look, there's the difference. So it has to be between C and D. Now, we know because this is obviously phosphorus, then the answer's got to be D. But if you look, just check. Look at the difference. We've added electrons, so that means it's negative. It's become more negative, not positive. Okay, so this one has to be D. Okay, question 13. Which of the following compounds has the most polarized anion? Right. Okay, so we're looking for basically something that's really polarized, so that we've got a big difference in charge. If we just write the charges of these, sodium, let's just do this in blue. Sodium is +1. Oxygen is -2. Magnesium is +2 because it's in group 2. Oxygen is -2. Potassium is +1 for 1 potassium. Oxygen is -2. Calcium is +2. Oxygen is -2. So what you're looking for is the biggest charge difference. So you can see the difference between these. There's a bigger difference between them two than any of the others. So we've narrowed it down to B and D straight away. The next bit you have to really understand about the size of the ion that's going to give you the kind of the charge difference, effectively. So the smaller the ion, the higher the charge density, and so that means it's going to have a bigger charge difference, or you're going to have a more polarized molecule. So magnesium, because it's higher up in the group, magnesium actually, or Mg2+, is a smaller ion than compared to something like calcium. Calcium is lower down the periodic table, and therefore it's a larger ion. Because it's a larger ion, its 2+ charge is spread over a larger area, so the concentration of charge isn't as great. So this means that actually the answer is magnesium oxide, because you have that much greater charge density, therefore you have a more polarized anion as well. So we're just going to write our answer. So our answer is going to be B. Okay, that's question 13. Right, on to the next question. So we've got... Okay, so question 14. The diagram shows the Born-Haber cycle for calcium chloride. It's not drawn to scale. All units are in kilojoules per mole. Okay, so which enthalpy change is correctly labelled on the diagram? Okay, so 3 of them are not correct and 1 of them is. Right, let's have a look then. So which enthalpy change? So we've got enthalpy change for the formation of calcium chloride, which is P. Right, let's have a look at P. There's P. That isn't the formation of calcium chloride. That is the lattice enthalpy. So this is lattice enthalpy is the formation of 1 mole of a compound from ions in the gaseous state. So that is not formation. So formation is actually this arrow. That's formation, because that's from elements in their standard states forming your solid compound. So it's not A. B, first ionization energy of calcium is Q. No, that's not the case. This is showing obviously 2 electrons have been removed, so that isn't the first ionization at all. So that one's incorrect. So it can't be B. C, electron affinity of chlorine, which is R. Again, no, because electron affinity of chlorine would be just 1 electron to 1 atom. This is showing adding electrons to both chlorines. So that isn't the electron affinity of chlorine, so that isn't right. So that obviously, by process of elimination, D is obviously right, but let's have a look at it. Twice the enthalpy change of atomization of chlorine. There it is. And yes, that's exactly what you would get. You've got Cl2 going to 2Cl. This is twice the enthalpy change because we've got forming 2 Cls. So that one is correct. So that one is D. Okay. Question B. So what is the value of X in kilojoules per mole, right? Okay, so there's the value of X. And what we have to do is basically just work out, we're going from here to here, and we'll have to work out that value. I like to see these as a bit like a roadblock. So if you're at this point here and you want to get to this point, but this road's closed, then what you have to do is take a diversion. You have to go up here, and then down here to get to that route. But obviously with this, we've got a load of arrows, and we have to obey the arrows as well, like little laws. So we have to make sure that we use the arrows to make sure we calculate these things properly. Okay, so right, let's just try it. So we're going from here to here, so we're going to go up here. And when we go with the arrows, we keep the signs the same. So this is plus 178, and that's plus 242. So what we're going to do, write the numbers in here. So it's going to be plus 178 plus 242 plus 1735, that one, and minus 692. So I'm going to add them as well. So it's plus 1735 minus 692. And then we've got the last step, which is basically going down to where we need to be, which is minus 2258. So we're going to put minus 2258. Okay, and then if we put all that in our calculator, we should get a value of minus 795. And so the answer is going to be B, minus 795. There it is. Okay, right, so on to the next question. This is question 15. So question 15 is obviously looking at some bond enthalpy data. So we're going to calculate the enthalpy change in kilojoules per mole for the reaction. Now with these, you just basically have to take into account all of your bonds. We'll do this in green this time, I think. So we've got a hydrogen, and we're going to react that with half an oxygen, but I'll show you what you do with that later on, and we're going to form water. Now, you just have to take into account all the bonds. So let's go for the hydrogen. Let's do this in blue. We're going to break this bond here. So because we're breaking it, that's going to give us the value of 436. It's an endothermic process. We need to put energy in to break that bond. The oxygen, right, this is where the half bit comes in. So we're going to do half times by the bond enthalpy for the O double bond O, which is 498. So half times by 498. Okay, and we're obviously going to add them two up. Now if we add them up, we should get 685. Okay, and then if we look on the other side, this one we're forming them. This is an OH bond. So an OH bond is 464. But because we're forming, bond formation is exothermic. It gives out energy. So the numbers we're going to use are going to be negative. So I'm going to change the sign in front of this number just to kind of make it a bit easier. So we're going to do 2 times by minus 464 because it's exothermic. And that should give us a total of minus 928. And all we have to do, this makes it a bit easier, is we literally just do that sum there. You've got your sum of it now. 685 minus 928. And then, so let's just put that there. 685 minus 928. And you should get your final answer as minus 243. Okay, so your answer should be A. Minus 243. Okay, question 16. That's the last question. Right, the chemical properties of an element are determined by its... Okay, chemical properties are always determined by the electron structure. So depending on, obviously, if it's got one electron, it'll behave differently from something which has 2 electrons in the outer shell. That's going to have an effect. The number of neutrons isn't. That's going to have an effect on, in terms of the mass of the element. Relative atomic mass, obviously that has an effect on mass. That's not going to have any effect. Number of protons and neutrons is basically the same as the atomic mass. So that's not going to have any effect. It is basically just electron structure. You just have to remember that. So that is obviously 16 is A. So there we have it. That's the end of the first 16 questions and the end of section A. So now we're going to have a look at the next question and section B. Okay, so this is question 17, section B. So it says this question is about the use of mass spectrometers. Bromine has 2 isotopes, bromine 79 and bromine 81. Explain the terms isotopes by reference to subatomic particles. Okay, right, you just got to know these definitions really. So an isotope is basically an atom with the same number of protons, but it has a different number of neutrons. So let's get that down on there. Nearly forgot that one. So atoms with the same number of protons but different number of neutrons. Okay, so that's pretty important. So there's your first mark. Right, 17b. Right, so we've got the presence and abundance of these isotopes can be determined by using a mass spectrometer such as that shown in the diagram below. So you can see we've got this lovely diagram here that's all been labelled. So it says explain how ions are produced in the area labelled A. Right, okay. The area labelled A is the ionization chamber. This is basically where, sounds very grand, doesn't it? This is basically where you've just got your sample that comes in and they are bombarded by electrons, which knock an electron off the atoms in the sample. And this creates a positive ion. So, right, let's get it down, because there's 2 marks here. So let's write this down here. So we say electrons are fired at the sample using an electron gun. Okay, so that's the first bit. That's what you would get for your first mark. And then you just need to give the explanation. So we need to say that this causes an electron to it causes an electron to be knocked off, forming an ion. Okay, so you get your 2 marks there. 2 sentences, 2 marks. So, okay. Right, part 2. State what is used to deflect the ions moving through the mass spectrometer in the area labelled B. Right, so there it is here. Look at this big thing here. This is a magnet or an electromagnet. What this does is it effectively deflects some of your sample through this bend here. So that's the deflection mechanism. So electromagnet or magnet would be fine. Okay, or we'll just put magnet. Anything like that will do. Alright, okay. Explain why there's a vacuum in the mass spectrometer. Right, it's really important to have a vacuum, because if we've got the mass spectrometer full of air, them air particles will interfere with the sample that's flying through the mass spectrometer. So having a vacuum basically just stops that interference and just allows the ions to move smoothly through the mass spectrometer. So let's put that on here. Will interfere with movement of ions. There we have it. Right. Straightforward so far. I hope so. Right. And then we get onto this. Spoke too soon. Right. So this is part C. So complete the mass spectrum below for a sample of bromine gas that contains approximately half 79 Br isotope and half 81 Br isotope. Right. Okay. So it says that we have to obviously put our different samples on here. Now, what would be really useful is to write down what isotopes, what fragments that we have going through this mass spectrometer, and then that will help us to identify where our peaks are and, crucially, how big the peak is as well. All this has obviously got to be relative to each other. So let's just have a look, have a think about what we've got. So what we could have is we could have bromine 79 as a positive charge, and we can get bromine 81, because obviously they were telling us about that, so that's fine. So this is where obviously the bromine molecule has actually been fragmented. It's split in half, and we've got an isotope, bromine 79 and bromine 81. Okay, remember all these things are positively charged. Sometimes though the molecule might not fragment, and it'll just go through as a double molecule, diatomic molecule. But obviously the bromine atoms can be made up of different isotopes, and so we've got to take into account each one of them, which is a bit of a pain, but we've got to do it. So right, let's have a look. So we could have a bromine, let's go for bromine 79 and another bromine 79. So let's imagine both isotopes, or both bromine atoms are bromine 79. Now we're going to put a positive charge on that one. So yes, so we need to obviously make sure we've got the mass of that as well. So if you add up, obviously 79 plus 79, that's going to be 158. Let me just put 79 on there. 81. That one's going to be 158. Okay. We've also got, we can also have a combination where we have bromine 81 and bromine 79. Let's keep that one the same. Positive. And also, actually, we can have it the other way around as well. Now, this is important, this bit. So let's put 79 there. And then bromine 81 there, positive charge. Now, for both of these, because they actually have the same mass, but they're slightly different molecules in terms of the isotope arrangement of them, we actually have quite a few of these. So these both are going to have a mass of 160. Now, that's going to be important when we draw a graph, because actually that's going to double the peak compared to these ones. Each one of these is going to give one peak, but because we've got two potential arrangements of this one, this is going to give a peak double as high or twice as high. And I suppose the last one is just bromine, both of them 81. So bromine, both 81, positive charge, and that's going to have a mass of 162. So basically what we've done is we've given all the potential options that you can have, fragmented and non-fragmented, and what we have are these numbers, and these are your peaks. But remember, this one's going to be twice as big because we've obviously got both two options there. So all we have to do is basically just draw our lines on there to show these fragments. So right, this is going to be a little bit interesting for me because I'm trying to draw it on a screen and keep it straight. So we're going to go for 79 first. So there's 79. Okay, so it's not too bad. And then we've got another one at 81. Now these ones are going to be the same height, because it says we've got an equal amount of them. So approximately half 79 and half 81. So because we've got equal amounts, then that's going to be they're going to be of equal height. We've also got a one at 158. So let's draw that in there. So 158 is going to be here. Okay, so let's draw that there. And then we're also going to get one at 160, but this 160 is going to be quite big. Now what I'll do is I'll put 162 next. So 162 would be that peak. And then you get one at 160, but this one's going to be twice as high as the rest of them. Okay, so obviously you can use the graph, the markings on the side here, when you've got it on paper, to try and make sure that it's to scale. But this one must be twice as big as the other one because you've got two potential options there. So basically, if you put bromine into a mass spectrometer, that is the spectra you get. It's 4 marks, so it's a decent number of marks. Obviously, it's making sure that you've got your peaks in the right place. And this one must be twice as high as well. That's really important. And they will be looking for obviously that being twice as high. Okay, right. Next one's part D. Calculate the relative atomic mass of bromine for a sample which was found to contain 47% bromine 79 and 53% bromine 81. Give your answer to 3 significant figures. Right. Okay, these are really relatively straightforward. All you have to do is you multiply the percentage abundance by the relative atomic mass of the isotope. So basically, it's going to be 47 times by 79 and 53 times by 81. And we add them two sums up and we divide it by the total percentage abundance, which would be, if we add these two up, that'll be 100%, obviously. Just be wary if it's not a percent and it's just a number. All you do is you add these numbers up and divide it by the total of them numbers, just to make sure it works. But these ones are in percentages, so that's fine. Okay, so let's work this out. So it's going to be 47 times by 79 plus 53 times by 81. Divide all of that by 100. And we should get 80.06. But we have to give it to 3 significant figures. So that 3 significant figures is going to be 80.1. So that's your answer. So you get your 2 marks. So you get 1 for obviously working out this bit, and then 1 for your final answer. Not that one. That's your final answer there. Getting your 80.1, making sure it's 3 significant figures. If it's not the 3 significant figures, you'll lose that mark. Right, part E. What would be the effect, if any, on the ME value of the peak if the ion detected had lost 2 electrons rather than 1 charge? Rather than 1 electron, sorry. Right. So remember, this is ME value. So this is a mass to charge value. So basically, let's say, for example, we had a mass which was 100, for example, and we had a charge of 1, so it just lost 1 electron. That would basically just be 100. But let's say if we had that same mass, I'll write it over here, same mass, which is mass of 100, but let's say it's lost 2 electrons, so it's got double charge on it. That's now going to turn that into 50, and you get a peak at 50 instead of at 100. So the effect would be halved, as you can see. So the value would be halved. Okay, right, nice and straightforward. I hope so anyway. Right, okay, so the next part. So this is part F. So for part F, you can see here that we've got one of the uses of mass spectrometers is for the detection of banned substances such as anabolic steroids in a blood or urine sample taken from competitors in sports events. Okay, so we're going to suggest 2 precautions that are necessary to ensure that the result of any analysis would be valid. Right, this is obviously quite common in if you're an athlete, you have drugs tests to make sure you're not using drugs which are banned, or you're declaring the drugs that you are using. So this is a bit like forensics. So with any forensics, you've got to be really careful with cross-contamination. You've got to be really careful about when you use the sample, when you test it, and recording the dates and storing it correctly. And all this stuff is really, really important because this sample can change over time if it's not stored correctly. So anything like, basically, there's loads of different things you can say here. So you can say the sample kept sealed. Obviously, that prevents any contamination. Sterile container. Okay, to prevent contamination again. Okay, we can also say we can use the sample may need to be tested immediately. Immediately. Okay. You could another one could be like sample stored and temperature control. So controlled environment. So anything like that. Obviously, I've put more than 2 there, but anything that would suggest that you keep your sample up to scratch and you make sure that it's it's stored correctly and you're not going to get any contamination or anything like that. Okay. Part 2. These substances can give competitors an unfair advantage. Suggest why the use of these substances may be of concern to the user. Right. Okay. Steroids, they have some quite serious side effects. Obviously, they're there to try and reduce the pain, so an athlete can run even when they're in pain, so they don't feel the pain. So they can enhance their performance. But obviously, side effects can be things like retention of water or fluids. They can have mood swings. They can suffer from depression, anger issues, etc. So there's a few things here that you can put here. It's mainly like biological, I suppose. So we're going to put anything like that. There's only 1 mark, so you just need to put one of these ones. Harmful side effects. Could be one. You could get things like depression. It's quite common with things like people taking steroids or steroid-based. Anger issues. They might get into mood swings. Might get quite aggressive with obviously the steroids. So yeah, anything like that, that'd be fine. Okay. And then suggest one of the use for mass spectrometers. Mass spectrometers are used really commonly. So they use things like space probes. So they took one up to Mars to go and try and detect water. So we'll put that on there. Obviously, probes. Make sure I spell that right. You can use it for carbon dating. So you can date certain things. So like trees, you can date skeletons in the ground. So archaeologists can use this. So it's quite useful for things like that. Also, you can use it for pharmaceutical purity testing and identification. So obviously, when you produce a drug, you want to make sure it's pure, so you can use that on there. Obviously, we can use it for relative atomic mass / relative molecular mass calculations, just like what you've done here. So anything like that. So they're used pretty widely. So yeah. Okay, so you get 16 marks for that, so it's not bad. So right, we need to go on to question 18. Okay, so this is question 18. This is about organic chemistry. So it says alkenes and cycloalkanes have the same general formula, but they react very differently with halogens. Give the general formula that applies to both alkenes and cycloalkanes. Right, so this is, you just have to remember this formula. It's really important that you do. This is just going to be CnH2n. So basically you've got twice as many hydrogens as you do carbons in these molecules. So this would be, this would obviously only be true if you only had one double bond, and cycloalkanes it would be. Okay. Part B. Using the structural formula, very important structural formula, complete the overall equation for the reaction of an alkene of your own choice, containing fewer than 4 carbons with a liquid with liquid bromine. If I can spit my words out right. We're going to name the product. Okay, so the product that we're going to form here is obviously going to be a haloalkane. I'm going to pick just ethane. It's ethene, sorry. Ethene is probably just a standard one, but it's going to have fewer than 4 carbon atoms. It just keeps it, they're trying to help you out there, keeps it a little bit simpler. But ethene's pretty standard. So let's go for CH2. It must be structural. So you can't put C2H4. You can't draw displayed with all the bonds. It must be structural. So it's CH2. They're very, very strict on that. And this is obviously going to, because you're adding bromine liquid, it's not bromine water, so it's bromine liquid, you're going to get both bromines adding across that double bond, you're going to get a dibromo compound. So let's draw our product here. So it's going to be CH2Br, CH2Br. Okay, so that's your structural product and our structural formula, and your name of the product is 1, 2 dash dibromo, and this is going to be ethane. Okay, make sure you put the comma between the 1 and the 2. It shows that you've got obviously a bromine on the first and second carbon. There's only 2 carbons anyway, but it's going to be dibromo, because di is telling you got 2 of them. So that's quite important. Okay, right, so we'll go on to the next question. Okay, so an example of an alkene with 6 carbon atoms is 2-methylpentaonine. It reacts with chlorine by means of an electrophilic addition reaction, and the diagram below shows a student's attempt at drawing the mechanism for this reaction. So there's the attempt. Okay, so there's a few mistakes there. Identify the 3 errors in this student's drawing of the mechanism. Right, I'm going to try and label this, I think, on the diagram, so it makes it a little bit easier for you to see. So we're going to look at error 1. Now the first error I can see is this. I'm just going to put a 1 there. This bit here, if you see, look at this chlorine molecule. Really, this is an induced dipole. So when this chlorine goes near an area with loads of electrons, like the double bond, the electrons move away from the double bond because you get repulsion. Now, what that means is you have a delta positive on the chlorine closest to the double bond, and a delta negative on the chlorine further away. Because what's happening is the electrons that were around this chlorine are now being nudged to one side of the molecule because of the repulsion with the double bond. So that's the first mistake. These polarities are back to front. They should be the other way around. So let's write this down in here. Chlorine. Okay, so it should be the other way around. Okay, this is like being a teacher. So marking these things, and so it's like your opportunity. So it's actually a really good skill, actually, marking up other people's mistakes, because you have to have a really good knowledge of obviously this yourself to be able to do that. So, okay, right, let's find the second error. So the other error, one of the classic ones here, and actually some students do make this error as well, and it's clearly a sign of lack of revision when they do make this error, but we have this arrow here. Now, curly arrows in mechanisms always go from an area of high electron density to an area of low electron density. Now you can see this arrow clearly is not going the right way. These arrows must go from the double bond to the delta positive, if that was the right way around as well, your polarity, to the delta positive chlorine. It always starts from an area of high electron density, and the double bond has loads of electrons, believe you me. So so we're going to write that mechanism there. We're going to write that answer there. Oh, I've got mechanism on the brain. Right, okay. So arrow goes from the double bond to chlorine. Oh, spelled that wrong. Right, okay. So there's the third one. That's the second one. Oh, right, get me brain in gear. Right, the third one. The third one is going to be. You can see here. This is quite a little bit more difficult to spot. Is this chlorine actually? The chlorine is supposed to have a negative charge on that chlorine, and you're supposed to have a lone pair on the chlorine as well, because the curly arrows. If you're drawing a curly arrow from an atom or an ion, you must show your lone pair or a lone pair of electrons, because that's where the curly arrow should start from. If you've omitted them, it's not technically correct. So for error 3 is going to be chlorine needs a lone pair of electrons. And a negative charge. Okay, right. So that gives you 3 marks. Obviously, the 3 errors there identified. And then part 2. The structure of the carbocation intermediate is correctly drawn. So that's one thing they've done right then. Explain why the positive charge is on the carbon atom shown. Right. You can see, there it is there. There's the carbocation. That is absolutely correct. That's fine. But what we need to do is we need to say why it's there. The reason why it's there and not anywhere else, for example here, is because this, having a carbocation or having a positive charge here, is better than on here, is because we've got a tertiary carbocation. We've got a carbon here, and carbon here. We've got 3 carbons surrounding this one here. Tertiary carbocations are much more stable than if the carbocation was on the end here, because this carbon's only bonded to 1 carbon. So that's called the primary carbocation. So these tertiaries are a lot more stable than your primaries. So that's why it's there and not on the end here. So, right, let's put the answer down there. Okay, there you go. So it's more stable, which is the tertiary one. So not too bad. Yeah, make sure you know your obviously your carbocations, because you do need to be able to use them and comment on them and talk about the stability of them, etc. Okay, right, next bit. So part D. There are 5 possible cycloalkanes, each containing 5 carbon atoms. 3 of the isomers are given below. Complete the other 2 boxes by adding skeletal formula of the other 2 structural isomers. Okay, so this is basically just making sure that when you draw these, they are different to the ones that you've already drawn. So, for example, obviously we've got a one there. Make sure it's got the same number of carbons and hydrogens, because these are structural isomers. So one of them could be this one. That one, so that one's got obviously your 3 within there, 4, 5, so it's still got 5, which is fine. And you can have another one which is still the 3, but instead of having a methyl group or 2 methyl groups, we can have an ethyl group hanging off the end there, because we haven't had one of them yet. So yeah, all these ones here are showing 2 methyl groups, but this one is 2 methyls coming off the same carbon. This one's obviously coming off different carbons, and this one is basically an ethyl group coming off, which we haven't had yet, so that's that one. Okay, so that gets you 2 marks. Right, define the term structural isomerism. I'm pleased they've asked this, because they've asked you to work that out without actually asking you to define it. So basically a structural isomer is something with the same molecular formula but a different structural formula. So you really do have to remember that one. So they've got the same molecular, if I can spell it right, formula, but different structural formula. Okay, to get 1 mark for that, not too bad. Okay, part F. Another example of a cycloalkane is cyclobutane. This compound, like other cycloalkanes, can also react with chlorine. The overall reaction of cyclobutane with chlorine is as follows, and given is the reaction there. This reaction can occur at room temperature and pressure. And what further condition is needed for this reaction to take place? Right, this is cyclobutane. So cyclobutane is obviously a cycloalkane. Trying to react anything with an alkane is a bit tough. Alkanes are pretty stable. They don't really have any, well, they don't have any polarity on there. They don't have any significant functional groups on there. So they're really, really stable and really difficult to react. So if you're going to react anything with an alkane, you need to use UV radiation, and you go via a radical mechanism. So just look out for that. Alkanes, any reactions with alkanes where you're trying to add something to it, generally you do have to use something quite severe like UV radiation to break that bond and get the reaction going. But using UV always creates radicals. So yeah, so this one's going to be UV radiation. Okay. And then it says, using the appropriate arrows, complete the equation for the initiation step of the reaction mechanism for the reaction of chlorine with cyclobutane. Right, so this is the initiation. So this is the starting of a process. So we start with a non-radical and we end up with radicals. So we use UV and it basically splits this bond homolytically. That means you have 1 electron going each way into each chlorine, but obviously it's an unpaired electron. So we've got 1 going this way and 1 going that way. Okay, so it's these fishhook arrows, these like single-headed arrows, so like that. So that's pretty important. Make sure you're not double-headed, otherwise you lose the mark. So it's single-headed. So you've got them going each way, and then what you form is 2 lots of Cl dot. So 2 Cl radicals. So you get 2 marks for that. 1 for your fishhook arrows, and 1 for you obviously putting 2 Cl dot there as well. So that gets a mark for that last bit there. Okay, right, on to the next part. Okay, so using molecular formula, write equations for the 2 propagation steps of this mechanism. Right, I suppose this was inevitable. Right, a propagation step is basically just where you've got a non-radical molecule reacting with a radical, and effectively what happens is you get a reaction and you get the radical moving from one molecule to another. And these radicals, remember, are really reactive, so they will just keep on reacting with pretty much anything. But there is a very specific order to this that we have to use. So right, so what we're going to do, the first propagation step is basically we have our alkane, or cycloalkane, which is C4H8. There's a cycloalkane. Them radicals that we made in the initiation step, that's Cl dot. That's now obviously going to get involved in the reaction because it's really reactive. And what's going to happen is the hydrogen from the cycloalkane is going to drop off. It's going to be pulled off this molecule here. And the radical is now going to be, instead of on the chlorine, it's now going to be part of this. And the chlorine is going to effectively react with the hydrogen. It's really unstable, remember. So it has to form, the chlorine has to be part of a molecule which is stable. In other words, a non-radical. So we're going to form HCl. But the radical can't just disappear. You can't just get rid of it. It's there. So this lone pair of electrons, a lone electron. So just a single electron. So this is going to be C4H7 dot. There's the radical there. Okay. Now, when you form the radical, this is how you know what your second step is. The radical from the first step, okay, must be the reactant in the second step. Okay. So we're just going to put that there. C4H7 dot. So that gives you a little bit of a hint. Now, because we're reacting this, and it's a propagation step, remember, so we need a non-radical, okay? Because we're reacting this to form a haloalkane, or halogenoalkane, we need something that's a non-radical that contains a halogen. Now, what that is chlorine. Now, this is a chlorine molecule which hasn't yet been split by UV. And we play this game of pass the radical again. Remember, this C4H7 doesn't want the radical, so it's going to react with the chlorine to form a non-radical, and the radical is going to be passed over again. So we're going to form, obviously, our haloalkane, H7Cl. But also, the product of the second propagation step must be the radical product of the second propagation step must be a reactant in the first step. So we've got to have Cl dot there. So this, basically whatever's here, must be the same radical as what's up there. So these little prompts help you to kind of make sure you're getting the right reaction, because I know sometimes these can be a bit confusing for some people. Okay, so you get 2 marks, obviously one for the first one, one for the second one. Okay, and then part IV, name the type of bond fission which occurs in these propagation steps. Okay, we did mention this just before. This is homolytic fission because we're getting one electron. Homolytic meaning the same. So, and lytic obviously means to break. So we're breaking a bond. So basically we're breaking it so we get one electron each side on each atom. So this is homolytic. Okay. And then V. There are also termination steps in this mechanism. Explain how these differ from the other steps in the mechanism and why these result in the reaction ending. Okay, so a termination step is where we have 2 free radicals reacting or colliding together, and what they produce is a non-radical product. So this is a bit different because all the ones that we've seen, the initiation and propagation, they've all involved a radical being produced or maintained. This is the only step where the radicals can be removed effectively. So we're going to write this down here. So we've got 2 free radicals react to produce a non-radical product. Okay, so you get 2 marks. One for saying you've got 2 free radicals reacting, and the second mark for saying that a non-radical product is made. So that's why they're a little bit different. Okay, and the part G, the last bit. So if the reaction with cyclobutane is carried out with an excess of chlorine, how are the products of the reaction affected? If you've got loads of chlorine, you're going to get multiple substitutions. So because there'll be loads and loads of Cl dot radicals all like floating around. So these radicals will then go and react with your haloalkane that you've just made in the propagation step, and they'll react and form a dihaloalkane and trihaloalkane. So they'll keep on reacting, and you get further substitution. So okay, so you get further substitution can occur, and obviously that gets to the last mark. So there we are. Right, so that is the end of question 18. So now on to question 19. Okay, so this is question 19. So it starts by saying sodium and chlorine react together to produce sodium chloride. The bonding in the product is different from that of both of the reactants. Evidence for the type of bonding present can be obtained in a number of different ways. Okay, so we'll start with A. Draw the electron density map for a chlorine molecule to show covalent bonding. Right, electron density maps mean you're basically just showing where the electrons are and how they're distributed. Now, chlorine is a non-polar molecule, so we're going to get this even distribution. We've got to show obviously the kind of where the electrons are located and where they are. Now with chlorine, obviously we've got different shells of electrons existing, and we obviously have a nucleus as well. So we need to identify them as well. So when we draw it, we need to draw effectively. We've got 2 circles to show how these things are mapped. But the outer electrons are involved in the bonding. So what we do to kind of show this, we show them kind of merged together. You might be able to draw this a lot better than I can. But just make sure that you're showing the merging of these electrons, and you show at least 1 circle in the middle of your diagram there to show obviously how the electrons are arranged around the center of the atom. Okay, so that gets you 1 mark. So pretty straightforward. Part B. Sodium chloride is ionically bonded. What is meant by the term ionic bond? Right, ready for this? Okay, so you've got to say electrostatic attraction between oppositely charged ions. Okay, that is just chemistry keyword overload there. Okay, the electrostatic attraction is basically the attraction between positive and negative, so that's the attractive force, and obviously oppositely charged ions, because you do have a positive ion and a negative ion, and that's what holds these things together. That is an ionic bond. So let's put that down there. So make sure you get all these keywords in. Okay, so this is an electrostatic attraction. Okay, between oppositely charged ions. So there you go, that gets you the 1 mark. Right, next bit, part C. So electrolysis is an experiment which you could carry out in a school or college laboratory on an aqueous solution of sodium chloride to provide evidence for the presence of ionic bonding. Draw a label diagram of the apparatus that you would use for this experiment, indicating how your results would show that the bonding was ionic. Right, so what you would what we're looking for is basically just a setup and a diagram, and so this is I suppose the classic sign of this is your you might have done this before, where you get a glass slide, like a microscope slide, and you put a bit of filter paper soaked in the ionic compound. You stick this to your slide, and you have crocodile clips, 2 crocodile clips connected to a battery or power source, and you also need, because this is sodium chloride is colourless, you need evidence to show that it is ionic. And one of the evidence is that it conducts electricity, allows the conduction of electricity. Now, to prove this, you're going to need something to tell you that it's conducting electricity, because you can't see it. So an ammeter or a bulb would do, and obviously if that moves, then it basically tells you that it's an ionic compound. So, right, let's draw this out then. So basically, we're going to have a cell, and this is going to connect round. Now, forgive my drawings, they are not particularly great. You can tell I was no artist. So you'd have something like that, and you'd have your bit of filter paper that sits in the middle of the glass slide, and obviously this is crocodile clipped onto the actual glass slide. So this is your filter paper. This is going to be soaked in, and this is sodium chloride solution. Okay, as long as it's got your solution on there. Obviously this is just a glass. This is just a glass slide. Okay, you have a wire going around the other side, and you'll need some form of method to know that a current is flowing through there. So like an ammeter or a bulb or anything like that. So we're just going to put a circle on there, and obviously connect it round to form a full circuit. So this basically gives you the proof that shows that the bonding was ionic, because if it wasn't ionic, that wouldn't move. Your ammeter wouldn't show a reading. So this is an ammeter. Okay, and yeah, and you got your glass slide with your filter paper with NaCl. Obviously, this is your power source. This is where you get your power from. So it could be a battery or a power pack or something like that. But yeah, you need to show your marks. You need to show that you've got something to identify that it is ionic, to show that a current is flowing. Make sure you're showing a full circuit. It must be complete with power. And obviously this mechanism here, where you've got your glass slide with your filter paper soaked in sodium chloride, make sure that it's on there as well. Okay, so that gets you all them 3 marks. Right, so not too bad. Okay, so so you've got part D. So part D, it says chlorine gains an electron when it reacts with sodium to form sodium chloride. Draw the dot cross diagram of a chloride ion showing outer electrons only. Okay, so this is not too bad, is it? Okay, so you got chlorine. Chlorine is in group 7, so it has 7 of its own electrons. I'll represent these with crosses. There it is there. Okay, but if it's an ion, it means it's gained an electron, so it's gained an electron from somewhere else. So let's just put that as a circle. And the key thing with ions is you put a square bracket round, negative charge on the outside, and that proves that it's an ion. Okay. Part 2. Give the formula of an ion from period 3 has to be period 3, that is isoelectronic with the chloride ion. Right, okay. Isoelectronic basically just means it has the same number of electrons as the ion that is the same as chloride. So it's not too bad. I mean, you could pick 2 different ones here. You've got to make sure it's got the same number of electrons. So anything like either S2- or P3-, either of them ions will have the same number of electrons as chlorine. So let's put that down there. So any of them answers will be fine. S2- and P3-. Just make sure they're sensible and they can actually be formed. Things like using silicon might not be a good idea because it can form. It's really difficult to get Si4-. So yeah, as long as it's sensible, then you can get that. So that's fine. E. Right, sodium and sodium chloride can both be good conductors of electricity. Under what conditions do these substances conduct electricity? Compare the method of conductivity in each case. Right, okay, so let's start with sodium first. So sodium is a metal, and like many metals, it will conduct electricity because it has free moving electrons or delocalized cloud of electrons above the positive metal ion. So sodium conducts when it's a solid, or even when it's a liquid for that matter, it will conduct. So put that on there. Okay, so that's fine. Sodium chloride, if we look at the compound, sodium chloride will conduct as well, and it will conduct when it's molten or when it's dissolved in solution. It won't do it when it's a solid, because the ions are not free moving, but it will when it's molten or when in solution. So we'll put that one on there as well. Okay, right. So that's fine. We've addressed both of them. Obviously, we're comparing the two, so we need to basically talk about the structure of them, like I said. So we've got delocalized electrons in sodium. They're charge carriers. They carry that charge across. And in sodium chloride, we've got free moving ions. So we're comparing why both can do that. So let's put this on here. Delocalized. So, and we have free moving ions in sodium chloride. Alright, so you get your 3 marks there, as you can see. You get 1 for saying sodium conducts when solid or liquid. Sodium chloride conducts when molten and when in solution, but not in solid. And the comparison of them is, obviously we've got delocalized electrons in sodium, and they're charge carriers, and we have free moving ions in sodium chloride when it's molten or in solution. So there you go. So quite a short question, that one, so only 10 marks, but that's the end of question 19. So on to the final question, which is question 20. Okay, so this is question 20, the final one. So it says the reaction of calcium oxide with hydrochloric acid is an exothermic reaction. So we've got the equation there. In an experiment to investigate this reaction, the following procedure was carried out. It's got 50 centimeters cubed of hydrochloric acid, concentration of 2 moles per dm cubed and excess, was pipetted into a polystyrene cup and the initial temperature measured using a thermometer with 0.5 degree graduations. The second step is 1.46 grams of calcium oxide powder was weighed out and added to the acid. The mixture was stirred and the maximum temperature measured. So you might have done this practical at school or college. So they're giving us the temperature increase, and then part A, calculate the enthalpy change in joules for the quantities in this experiment. Assume that the specific heat capacity of the solution is 4.18 joules per gram per degree C or per C. Use this expression, so energy transfer in joules is 50 times by specific heat capacity times by the temperature change. Okay, so that's pretty useful because they've given us a lot of this actually. So right, let's just work it out then. So the energy transferred we know is 50.0. I'm going to multiply that by the specific heat capacity was 4.18, and we're going to multiply that by the temperature change. So you're just doing 35 degrees minus 19.5 degrees. And that should get you 15.5. And that's your temperature change. And then you put all that into calculator, you should get your energy in joules, which should be 3,239.5 joules of energy. So that'll get you that mark there. So not too bad. Okay, part B. Using your answer for part A, calculate the molar enthalpy change for the reaction between calcium oxide and hydrochloric acid. Include a sign and units in your answer. Right, so this is a molar enthalpy change, or also known as delta H. So we need to work out the number of moles, obviously, of calcium oxide. The number of moles of this whole reaction. So we've got moles equals... and we've got the, obviously this is going to be mass over mR. Now the mass that we used of your calcium oxide was 1.46 grams. So we're going to put the mass there, because obviously moles equals, let's just put the equation on here just to make sure we're really clear, mR. So the mass is going to be 1.46 grams divided by the mR. Now the mR of your calcium oxide, if you use your periodic table to work that out, you should get an MR of 56.1. And then if you put that into a calculator, you should get the number of moles to be 0.02602. Okay, so now we know the moles, we have to work out the molar enthalpy change, also known as delta H, as you might see that. Now, because enthalpy is measured in kilojoules per mole, the formula we're going to use... I'll just put that there, kilojoules per mole. So obviously, using the units, we can work out the formula. So kilojoules is a measure of energy. So that's going to be energy in kilojoules divided by the number of moles. Okay, so that's how easy it is to kind of come up with these formulas. Just look at the units that you're going to work out, and that'll tell you what the formula is. So energy, in this case, was... now we've got to convert this into kilojoules. So there's the energy there. This is in joules. To convert it to kilojoules, we divide by 1,000. So we go 1, 2, 3 places back. And this is going to be 3.2395. And that's, remember, that's in kilojoules. Divided by the total number of moles, which we just worked out there, was 0.02602. Now, obviously, we'll get our answer. You put your number in, which should give you 124.5 kilojoules per mole. Okay. Now, the most important thing with this is the sign. We need to include the sign for this. So we know the units. Now, this reaction is warming up. So we start at 19.5 and we're going to 35. So this is an exothermic reaction because we're producing heat. And all exothermic reactions have a negative sign in front of them. So make sure you put that negative sign on there. If you miss that negative sign out, you lose a mark. All for the sake of just a minus sign. So yeah, it's exothermic, gives out heat, so it's negative. So just look at the temperature change. If the temperature's going up, then obviously it's going to be an exothermic reaction. Okay, right, on to the next question. Part C. The standard molar enthalpy change for the reaction between calcium oxide and hydrochloric acid is minus 196.8 kilojoules per mole. Suggest 3 reasons why the calculated value in part B is different from this value. Right. There's a number of reasons. Things that can, obviously we'll look for 3 reasons here, but things that can obviously affect the the temperature or the loss of energy or the difference is mainly because we might have lost heat to the surroundings. Obviously that can have an impact on the calculated value that you get from your practical in comparison to the theoretical value, what you should get. Also, anything to do with things like you might get inaccurate thermometer readings and things like that. So, right, let's start and write these down. So, reason 1, we've got heat loss to the surroundings. Okay, so that's 1. Also, inaccurate thermometer readings. Obviously, we're not reading the thermometer correctly, or where the thermometer is slightly out. But if we're not reading it properly, obviously that can have an effect as well, because that is dependent on that. So, all right, and then the third one as well. Your compound that you've used, calcium oxide, might not be pure. It might have some impurities in there. Calcium oxide can absorb a lot of water from the atmosphere, and so obviously that's going to have an impact on obviously on how the reaction is going to go, and the mass of calcium oxide that was used as well. Obviously that's going to have an effect on the enthalpy change. So yeah, so you might not have like 100% pure calcium oxide. So let's put that on there. Okay, so calcium oxide is impure. We can say that moisture absorbed from the air. Okay, anything like that. Okay, so they get you obviously the 3 marks there. Okay, right, part 3. Using the standard enthalpy change of minus 196.8 kilojoules per mole, calculate the minimum mass of calcium oxide that would be needed to raise the temperature of 250 centimeters cubed of hydrochloric acid, which is in excess, by 25 degrees Celsius. Okay, so what we have to do is ultimately work out the number of moles of our substance, because if we know the number of moles, we can then work out the mass, because obviously we know the relative atomic mass or relative molecular mass of calcium oxide. So we need to work out the number of moles, and to do that, we know the enthalpy change, kilojoules per mole, but if we work out the kilojoules bit, so the energy bit, and divide the two to cancel these units out, we can find out the number of moles. So our first step really is to work out the energy that this reaction produces. They've given us some numbers here. So we're going to use that formula that we had before, that was shown before, which is Q equals MC delta T. M's the mass of the liquid, so it's 250 centimeters cubed. We'll assume the density is just 250 grams for every centimeter cubed we have. C is the heat capacity, which is the 4.18, and the temperature change, obviously they've told us, raised it by 25 degrees Celsius. So let's stick these numbers in. Q is just energy, it's the symbol we use. It's handy that they use letters that obviously matched what it is we're working out. This is an energy, we use letter Q, but anyway, right, 250 centimeters cubed. This is like mass, we can say that's 250 grams. We assume the density is the same as 1 gram per centimeter cubed. The heat capacity is 4.18, and we're going to multiply that by the temperature change, which is 25. Now, if we put that into our calculator, we should get an energy of 26125 joules. Okay, convert that into kilojoules, and we should get 26.125 kilojoules of energy that's produced by this reaction. Now, like I said, we need to work out the moles. Now, to work out moles, what I can do is we can take, if we obviously to work out the moles of something is just mole. Now, to do that, what we could do is we could divide our energy, which is in kilojoules, divide that by this, which is the enthalpy change. And if we cancel out them kilojoules, we can get moles. So I'll show you what I mean. So the number of moles is going to be obviously 26.125 kilojoules divided by, so this is the energy that we've just worked out, divided by the enthalpy change. So, which is 196.8 kilojoules per mole. Now, this is where the brilliant thing is. So, if you see on here, look, I cancel them kilojoules out. I'm left with mole. That can jump up on there, and that effectively turns that into just standard mole. So that's why that's how we can work out the number of moles from that. So it's brilliant once you know how to kind of work the units effectively, and you know what formula is, because obviously that's quite a tough question, because you have to come up with the formula, derive the formula yourself from these values. So anyway, so we've got that there, and if we put that into our calculator, we should tell us the number of moles. So the number of moles should be 0.132749 moles. Okay, that's the number of moles. And then once we've done that, we can then work out the mass. So obviously the mass is just the number of moles times by the MR. So mass equals the number of moles is 0.132749 times by, now the MR of your calcium oxide is 56.1, so you can use your obviously your periodic table to work that out, and then you should get a total mass. So your mass should come out at 7.45 grams, and that should be your final answer. Now you get 3 marks for this, so you do get a reasonable amount of marks. So you get 1 obviously for working out your energy, 1 for working out the number of moles, and then 1 for working out the mass here. So you get 3 different bits here. So again, it's not too bad. So once you once you know what you're doing. Right, on to the next bit. Okay, so this is part D. Right, so part D is looking at the reaction of calcium carbonate with hydrochloric acid. It has the following standard molar enthalpy change, and you can see obviously that's minus 18.8 kilojoules per mole. This value can be used with the enthalpy change for the reaction of calcium oxide with hydrochloric acid to determine the enthalpy change for the thermal decomposition of calcium carbonate. This cannot be measured directly, so we have to use a Hess cycle. So we're going to use complete the Hess's energy cycle below by adding the missing arrow and entities. Okay, so use the cycle and the standard enthalpy change for the reaction of calcium oxide and hydrochloric acid, which is minus 196.8 kilojoules per mole, to determine the standard enthalpy change for the decomposition of calcium carbonate. Right, so there's a load of stuff to do here. Right, okay, I suppose the first thing we have to do is to write down our products. Okay, we need to know obviously what we're producing here. So let's look at if we take calcium oxide and carbon dioxide. Now, if I react that with 2 lots of HCl, what I'm going to form is, because calcium oxide is obviously a base, and I react that with HCl, which is an acid, we're going to form a salt, and the salt is going to be calcium chloride. So that's going to be one of the products here. Whoops. There you go. CaCl2. Okay. Now, calcium chloride, this is aqueous. This can be dissolved in solution, so that's aqueous. With this reaction, obviously, we're going to produce calcium chloride. It's salt plus water, so we produce water as well. Obviously, water is a liquid. And obviously, we have carbon dioxide as well. This is not going to get involved with the reaction, so we still have it present. So we're going to put carbon dioxide there, and obviously, that's a gas that's being produced. Okay, so there's the kind of the base bit there. This reaction is obviously, this reaction is showing the standard enthalpy change for the reaction of calcium oxide and hydrochloric acid. We have to determine the enthalpy change for decomposition. Because this is forming it, this is calcium oxide going to carbon dioxide forming these products. This arrow, to form this arrow is going to have to go downwards because we're producing these products here. When we react calcium carbonate with hydrochloric acid, basically, which is this, we produce calcium chloride, water, and carbon dioxide. So acid plus carbonate forms salt plus water plus carbon dioxide. So the arrow is going to point downwards because these are products from this reaction. Okay, so that one's going to point down. I'm going to put 2 HCl here because that's what we're going to react. 2 HCl to produce these products here at the bottom. Right, so that's the cycle completed. Now what we have to do is use the cycle and the standard enthalpy change for the reaction of calcium oxide and hydrochloric acid to determine the standard enthalpy change of decomposition of calcium carbonate. So we want to work out this value here. Okay, now they've told us some numbers. They've told us the decomposition, or the reaction, sorry, of hydrochloric acid. There you go. Calcium carbonate with hydrochloric acid has the following standard molar enthalpy change. So this one is minus 18.8. So we know this one is just, I'll put this in a different colour, minus 18.8 kilojoules per mole. And we've also been told that the standard enthalpy change of reaction of calcium oxide and hydrochloric acid, so this bit, and hydrochloric acid, is minus 196.8 kilojoules per mole. So we're going to put that there. Minus 196.8. Okay, so that's told us obviously that value there. And then what we have to do is basically we just need to work out this bit here. That's what we need to work out, which is the decomposition. So here we go. Start from here. We're going to here. Okay, the arrow's telling us to go this way. Treat it like a roadblock. So imagine this is a road and you can't go that way. You have to go this way and then that way to get to the destination where you need to be. Now, if you go with an arrow, you keep the sign the same. If you go against an arrow, you change the sign. So we're going to start from here. I'm going to go down this arrow. So that's going to make it have minus 18.8. Okay, let's just draw that 8 again. So 18.8, and then we're going against the arrow here. So we keep the number the same. Number doesn't change, but the sign does. So we're going to put plus 196.8. Okay, and then obviously this is the delta H bit, and then if we put that into our calculator, we should get a value of plus 178 kilojoules per mole. Okay, so obviously we've got our answer there. We're going to put this down here, so that's plus 178. Whoops, we've still got the units already there, so that's kilojoules per mole. And obviously that is that value there. And a good way of checking to make sure it's right, if you start anywhere on this cycle, then you should have, the whole thing should add up to 0, basically. So if we start from here, so we go with the arrows, that's plus 178, minus 196.8, plus, because we're going against the arrow, 18.8, then it should all add up to 0. So just check it after you've done your cycle. But yeah, you get quite a few marks there. You get 4 marks. 1 for getting that bit right, 1 for your stuff in the box is correct, 1 for this bit for using the cycle, and 1 for actually getting your answer correct as well. So you get 4 marks. So it's yeah, pretty generous. You know, any mark will count. Okay. Right, and on to part 2, which I believe, yeah, this is the very last question, so just 1 mark for this one. Right, complete and label the enthalpy level diagram below for the series of reactions in D part 1. Your diagram does not have to be to scale. Right, so remember in the previous diagram, we're forming calcium carbonate, or we're using calcium carbonate to produce your products, and also we're using these ones to produce the same product. So remember, if I go back up, there it is. Look, there's your calcium carbonate, there's your calcium oxide and carbon dioxide. Both of these are being used to produce these products here. So when we produce our diagram, it has to be arrow pointing down from this lot and from this lot. So let's draw that in. Once my computer finally boots up. Right, we've got to, obviously the products are more stable than any of your reactants. So you're going to form calcium chloride plus carbon dioxide plus water. Okay, and we're going to form an arrow going down from here to here. So that's lower in energy. It's the enthalpy, that's a negative enthalpy change. And this one, that one points down to there as well. So you can see, there you go, that shows it there. These are negative, look at these 2 numbers. These are both negative, so that's how I know that this line is below both of these. These are both giving out energy. So our energy must be, in this energy profile diagram, must be the same as well. Look, they're both negative enthalpies. So that's why this line is below there. because that symbolises the both negative enthalpies. So there we go. That's the answer to that one. So it's only worth 1 mark, but you basically just drawn 2 arrows on a line and writing the equation there. But there we go. That's the end of the paper. As you can see, it's 14 marks for that question. I suppose things you just need to take away from this: make sure you're reading the questions really, really carefully. Again, I can't emphasise that enough. You've seen a few here where it could have been slight pitfalls. Make sure that you give your numbers the right degree, significant figures. I suppose your enthalpy level diagrams, make sure you're using Hess's law. Use the little trick to check the Hess's law is done correctly by adding up all the numbers. They should add it to 0. And yeah, your multi-choice, just make sure you double check your other answers as well. Probably the best thing with multi-choice is to cover up the answers and then basically try and see if you can come up with the answer for yourself, and then check your answers, check the multi-choice options and go with it. But yeah, that's it. Hope that helps. Bye bye.